Welcome to this section on steam quality. Steam should be available at the point of use in the correct quantity, at the correct temperature and pressure, free from air and other incondensable gases, clean and dry. This section will highlight the importance of these criteria. The correct quantity of steam must be made available for any heating process to ensure that a sufficient heat flow is provided for heat transfer. In a similar way, the correct flow rate must also be supplied so that there is no product spoilage or drop in the rate of production. Steam loads must be properly calculated, and pipes conveying steam must be correctly sized to achieve the flow rates required. This will be discussed in detail further ahead in the sizing section. Steam should reach the point of use at the required pressure and should provide the desired temperature for each application. Otherwise, performance will be affected. The correct sizing of the piping system will ensure this is achieved. This will also be discussed in detail further ahead. For now, keep in mind, even if the pressure gauge is correctly displaying the desired pressure, the corresponding saturation temperature may not be available if the steam contains air or incondensable gases. Air is present within the steam supply pipes and equipment at startup. Even if the system were filled with pure steam the last time it was used, the steam would condense at shutdown, and air would be drawn in by the resultant vacuum. Take a look at the following steam-jacketed chemical reactor. Here, when steam enters the system, it will force the air towards either the drain point or to the point furthest from the steam inlet, known as the remote point, as seen here. Therefore, steam traps having a sufficient air venting capacities should be fitted to these drain points. A typical example is now shown on screen. In addition to this, an automatic air vents should be fitted to all remote points, as seen here. However, if there is any turbulence, the steam and air will mix, and the air will be carried to the heat transfer surface. As the steam condenses, an insulating layer of air is left behind on the surface, acting as a barrier to heat transfer. The effect of this barrier on heat transfer will be illustrated in a later video. For now, keep in mind, in a mixture of air and steam, the presence of air will cause the temperature to be lower than expected. To better illustrate this important concept, it is important to recall that the total pressure of a mixture of gases is made up of the sum of the partial pressures of the components in the mixture. This is known as Dalton's law of partial pressures. The partial pressure is the pressure exerted by each component if it occupied the same volume as the mixture. For a mixture of air and steam at a given pressure, the effective steam pressure expressed in bar absolute equals the amount of steam as a proportion of the total mixture by volume times the indicated pressure expressed in bar absolute. Okay, now consider a steam-air mixture made up of 3/4 steam and 1/4 air by volume. The total pressure, as indicated by the pressure gauge upstream of the chemical reactor, is 4 bar absolute. If this was 100% saturated steam, then from the saturated steam table, the expected saturation temperature would be 144 degrees Celsius. But this is not 100% steam. This is a mixture of air and steam. So we expect the temperature to be lower than 144 degrees Celsius. So let's determine the actual temperature of the steam. First, we will use Dalton's law of partial pressures. Here, the amount of steam in the mixture by volume is 3/4, 75%. Thus, the effective steam pressure is 75% of the total pressure. So, 75% of 4 bar absolute. This gives 3 bar absolute as the effective steam temperature. Let's use the steam table to determine the saturation temperature of steam at 3 bar absolute. As seen here, the saturation temperature is 134 degrees Celsius. Therefore, the steam only has an effective pressure of 3 bar as opposed to its apparent pressure of 4 bar. The mixture would only have a temperature of 134 degrees Celsius rather than the expected saturation temperature of 144 degrees Celsius. That's a 10 degrees Celsius difference. This phenomena is not only of importance in heat exchange applications, where the heat transfer rate increases with an increase in temperature difference, but also in process applications where a minimum temperature may be needed to achieve a chemical or physical change in a product. Air can also enter the system in solution with the boiler feed water. Makeup water and condensate exposed to the atmosphere will readily absorb nitrogen, oxygen, and carbon dioxide, the main components of atmospheric air. When the water is heated in the boiler, these gases are released with the steam and carried into the distribution system, as depicted here. Now, atmospheric air consists of 78% nitrogen, 21% oxygen, and residual amounts of carbon dioxide by volume. However, the solubility of oxygen in water is roughly twice that of nitrogen, while carbon dioxide has a solubility roughly 40 times greater than oxygen. This means that air dissolved in the boiler feed water will contain much larger proportions of carbon dioxide and oxygen, both of which can cause corrosion in the boiler and the piping system. To reduce the phenomenon of corrosion, the temperature of the feed tank is maintained at a temperature typically no less than 80 degrees Celsius, so that oxygen and carbon dioxide can be liberated back to the atmosphere, as the solubility of these dissolved gases decreases with increasing temperature. The concentration of dissolved carbon dioxide is also kept to a minimum by demineralizing and degassing the makeup water at the external water treatment stage, as seen here. Layers of scale found on pipe walls may be either due to the formation of rust in older steam systems or to carbonate deposit in hard water areas. Other types of dirt which may be found in a steam supply line include welding slag and badly applied or excess jointing material, which may have been left in the system when the piping system was initially installed. These fragments will have the effect of increasing the rate of erosion in pipe bands and the small orifices of steam traps and control valves. For this reason, it is good engineering practice to fit a pipeline strainer. A typical example of this is now shown on screen. This should be installed upstream of every steam trap, flow meter, pressure reducing valve, and control valve. In this steam pressure reducing station, two strainers are used, one upstream of the control valve and a second one upstream of the steam trap. In a strainer, steam flows from the inlet through the perforated screen to the outlet, while steam and water will pass readily through the screen. Dirt will be arrested, as seen here. The cap can be removed, allowing the screen to be withdrawn and cleaned at regular intervals. When strainers are fitted in steam lines, they should be installed on their sides so that the accumulation of condensate and the problem of water hammer can be avoided. This orientation will also expose the maximum strainer screen area to the flow. Okay, now keep in mind a layer of scale may also be present on the heat transfer surface, acting as an additional barrier to heat transfer. Layers of scale are often a result of either incorrect boiler operation, causing impurities to be carried over from the boiler in water droplets, as seen here, or incorrect water treatment in the boiler house. The rate at which this layer builds up can be reduced by careful attention to the boiler operation and by the removal of any droplets of moisture. The different ways to achieve this are discussed further ahead.